Hey everyone, welcome to today's video. Let me ask you a question. Whenever you are using the internet drops packet all the time. The packets can be lost, it can be delayed, it can be duplicated, or it can be arriving completely out of order. But whenever you are downloading a file, it arrives perfectly every single time. Why it does not arrive broken or corrupted? How exactly is it possible? Have you asked this question anytime? The answer is a protocol in the internet, which we call it as a TCP. TCP does something remarkable. It takes an unreliable network and turns it into a reliable communication stream. In this video, I want to show you how exactly it is being done. Because every time you search for TCP, you will always land on three-way handshake and you end up understanding it is three-way handshake. But TCP is beyond that. In this video, we will understand the actual mechanics, the algorithm, and the math behind it. Because once you understand TCP, the way you debug your slow system will be completely changing. So without any further delay, let's jump into the topic. So in this video, we will break the concept into couple of steps. First, we will try to understand why TCP even exists in our life. Then we will try to understand the handshake process and we will understand what exactly the latency takes is. Then we will jump into the actual algorithm, one of the algorithm, which is flow control, followed by understanding the slow start. Then we will understand what exactly the sawtooth, how it comes into the existence and how it helps in our TCP. Finally, we will understand the bandwidth delay and we will try to break down each concept in a very simple way. So during 1974, there were two engineers, Vincent Cerf and Bob Kahn. They were trying to solve a very impossible problem during that time. So they were trying to figure out how do you connect completely different networks, how you can connect radio links, satellites, copperware into one internet. So that answer came in a single paper, which was called as the Protocol for Packet Network and Intercommunication. You can read about that paper. I can give you in the description box. So in that paper, there were two RFCs, RFC 791 and RFC 793 during 1981. And RFC 791 became IP and RFC 793 became TCP. IP stands for Internet Protocol and TCP stands for Transmission Control Protocol, as you know. What exactly is this? So Internet at the lowest level runs on IP and it is very simple. And the main job of IP is to move one packet or move one packet from one machine to another machine, which is something like moving a package from one location to another location. But it will not give you a guarantee. It may reach to the destination or it may not reach in between, or it can disappear in between somewhere in the network, right? Or it can be dropped by a router or it can be lost in congestion. It just doesn't care. Application cannot live with this uncertainty. If you are transferring a file or loading a web page or making a database query, you need the data to arrive in full order. It cannot be broken. So TCP sits on top of your IP and it adds everything which IP does not provide. And TCP is a reliability layer. And you can consider TCP is that postman which takes your package, it goes to your destination, it asks for your receiver, his name, and it takes his sign in a paper and delivers that packet to your receiver, whoever you have asked to receive. So that reliability layer TCP provides you when you are transferring your packet in the internet. When it comes to the working functionality of both the protocols, IP thinks in packets, but TCP thinks in, right? So whenever your application sends data, TCP sees it as a continuous stream of bytes and it then breaks that stream into segments and each segment gets a sequence number. How exactly? For example, if you consider this as a stream, maybe your data, it has been segregated into multiple streams. It thinks as a single stream of data and it tries to segregate into multiple segments. In this example here, you can see there's a segment 1, segment 2, segment 3. This is the numbering system which TCP does to your data or a stream within your data so that your data is not lost. Every data in your stream or every byte in your stream has a sequence number and it is the unique identity for your sequence which is getting transferred over TCP. Why this is important? For example, if your segment or one segment of your data is not getting delivered to the receiver end, which happens most of the time, it is an obvious case, the receiver can reconstruct this sequence based on this numbering with the original data and it can match the data so that the data is getting delivered perfectly because it knows exactly where each piece is belonging based on this sequencing and it tries to reframe this or rearrange this within that particular sequence before receiving it their receiver end. So that is why this segmentation is very important in your TCP. So that is about your handshake process. All these things happens under the hood. I'm not telling the three-way handshake is not the right way of understanding the TCP. The sequencing and the stream segmentation into segment is very important, which happens under the hood. Before your three-way handshake comes into the picture, this is what happens under the hood. You have to understand. So every time receiver successfully gets the data, it sends an acknowledgement or send a X signal to the sender, right? And X says, I have received up to X byte and send me the next one. The sender again keeps a timer for every segment it sends. And if the ACK is not coming back, then it assumes that a segment was lost and retransmit that particular. How exactly it works? As you know, each time if a sender is there, first what it will do, it will try to send a SYN request to the receiver. And let's say that value is X, which is nothing but your sequence number. And it is taken in the random order from the receiver end or the server end. Once the receiver receives it, finally, it creates a ACK along with SYN. What it is? So SYN value was X. And what it does, once it is received, it will increment with the value of 1. Why it is important? Because it doesn't have to be duplicated in the network layer, right? So that is why it tries to increment with a number 1 and it creates a signal with the number X plus 1. And it again creates a value of Y with acknowledgement with a random value, which is auto-generated or auto-populated from your server. And the same SYN and ACK, it goes to your sender again with Y plus 1 and X plus 1. When it receives the sender, it again gets incremented with plus 1 and it gets a sequence Y plus 1 and X plus 1 with the acknowledgement which is this sender has received. Now this value is Y plus 1 and X plus 1, right? And what will do? Again, it will flow the data or application data to the receiver. And this particular sequencing will be keep on happening, right? That is how your three-way handshake works and the CNAC principle works in the TCP transmission, right? So now the question is that what exactly is the latency tax? Okay, it is a very important point. So whenever you are sending a data from your application to your receiver, it has a time to travel, like, it takes some time to receive. Let's say the sender is in London and the receiver is in New York. So receiving from London to New York, there will be a time to travel, right? So let's say that time may be 84 milliseconds. Okay. So before it reaches, the overall packet gets reached. Between that, there is a drop in the network itself, right? What is that drop? So every signal which sender sends to the receiver, it takes some time to reach. For example, in this scenario, it may be 28 milliseconds to reach from London to New York. And the same thing happens when it goes back from the receivers to sender, maybe 28 seconds or 28 milliseconds. So this is the tax or minimum time which the communication or the handshake has to happen. This out of 84 millisecond, which is the total time to travel, out of that 50-second millisecond will be substituted and the remaining will be calculated accordingly. So what does it mean? So for example, let's say you are troubleshooting an application and somebody has complained that the application is slow or there is a lag in delivery or something is not right. Most of the time, what you think is there may be CPU problem, memory problem, or whatever might be the hardware problem, you might be thinking that. But always that is not the case. Whenever you are trying to troubleshoot, you should start with your networking layer and you will try to understand what is the latency between it. If the latency is 2 minutes, which means to receive the data, if it is taking 2 minutes, then there might be the latency tax which is included in this 2-minute time, which you have to take consideration of that. So if you are taking that consideration, it makes you troubleshoot more deeper so that you don't unnecessarily blame some other factors like CPU, memory, and etc. doing that. So this is why it is very important, and understanding in the TCP concept also, it gives you more room for troubleshooting. So that is about your latency tax. Now we are getting into some of the concepts which is working under the hood or helping the algorithm to build or make the TCP work more efficiently, right? So three-way handshake is a method which happens, but there are other scenarios as well. What are the scenarios? For example, let's say you are sending a data from a sender to receiver. Let's say your sender is a high power server which has a lot of capacity and it is blasting data at full speed to the receiver. But if the receiver is very small device or it has a limited space, limited disk size, or limited capacity, the packets which it is received, it can suddenly fill up the buffer space, right? And it can drop and it can result to a performance issue as well. So to avoid this kind of scenarios, TCP protects the receiver from getting overwhelmed with a concept called as flow control. How exactly it works? So before sender sends the data to the receiver, so what receiver does, it populates a window size, or we call it as RWND. What exactly it is? So RWND is a size or a function which sender will understand, and it will try to match that particular window size, and that window size it will be used to send that. For example, let's say receiver has only capacity to receive 5 kb per second, so that you can consider as a window size, and the sender will send in that speed only because it cannot take more than that. How exactly? So in the state one, what it will do is it will try to send, for example, let's say it has told that there is 48 kb, it is free, and the receiver will send in that speed only. In the state 2, what it will do is, let's say there is the buffer size is getting decreased, and there is only 8 kb is free, and during that time the r wind is 8 kb. So similarly the sender will be sending in the r kb per second speed only. Finally, in the if the buffer is completely full, for example, it will tell that rwnd is completely 0, and the server will be completely pausing, and there will be a drop in the transfer, it can occur as well. So that is how exactly the flow start works. And whenever the sender knows it that the rwind size, it will always stay in that particular window, it will not go beyond that, because if that window is getting shrink, the sender will be slow down. Now you might be asking, like, why I should know about flow control, why exactly it does matter when I'm learning about TCP, right? So flow control can tell you if a sender is slowing down or is not receiving the data, or it is slowing down the receiving process. Even if the network is fine, you can consider the flow control is the reason, because as an SRE it can help you to spot throughput issues caused by your slow, and the issue that there is a flow control which is occurring that because your application server has crossed the buffer size, or there is a very less space which is left for receiving your packets. So that is why your application server or your whole app has slowed down, and you can troubleshoot accordingly, because most of the time the network is not the issue, it may be the flow control which is blocking the transfer, and it can be something which is underlying in your application or within your server to receive the packets from the sender. Hope that is clear. So now comes the slow start. So slow start is a combination of multiple algorithms which helps TCP to make that reliable connection. So while your flow control can help the receiver or save the receiver from getting overwhelmed from the excess sending of the packets, but what with the network? If network is having a congestion, or your router is having some problem for which the data cannot be transmitted or your packet cannot flow, in that case, how TCP can function? That may be the question, right? The answer is slow start. So slow start is basically a combination of multiple algorithms, which normally we divide it into two. One is your congestion control, one is your congestion avoidance. How exactly it works? For example, let's understand if you are transmitting a packet from your New York to London, right? So in between, there might be so many network hiccups can happen, but how you will ensure that your packet is getting delivered in London without any problem, right? So what TCP does, it does a concept called a slow start. What is the slow start? The starting point is the algorithm we known it as congestion control. What exactly it does? So what it will do, it will continuously try to probe the network, and if it is looking that the network is completely fine and it can transmit the data, instead of sending all the data or all the sequences or segments at a stretch, what it does, it tries to start slow. So what it will do, first it will try to send 10 packets, right, at the first round trip, which means one handshake, second handshake, and third handshake. It will try to send 10 segments. If it finds that, okay, it has been receiving nicely, so what it will do, it will try to double it in the next handshake, because handshake process is a continuous process, right? So in the next time, what it will do, it will try to send 20 segments. If it has received or reached in the same time, then what it will do, again, it will try to increment that. How? Again, it will double it. So it will keep on doubling the size of the segments while sending in each round trip, right? In each handshake, it will try to double it. So that process, we call it as congestion control, and it will keep on doing until unless your network is not getting dropped, or which we call it as the state of packet loss. Let's say in between your packet got lost, or there is some network problem for which your packet is not getting transmitted as it was doing up to this level. So once it is reached that level, we call it as packet loss, right? So from here, there again, one more algorithm gets introduced, which we call it as congestion avoidance. We'll get into that. But before that, so why this state or this two different algorithm is very important. So when you are transmitting the packets with the help of TCP, TCP's work is to deliver it completely without getting lost or without breaking any of the flow. So what it does, instead of completely taking it to zero, instead what it will do is it will slowly get drop into a certain position, let's say this position, and from there again it will try to send the packet slowly. From this again it will try to send the packet slowly. From this one, let's say if it has reached to 160 level, from 160 level what it will do is it will completely half. From this it will reach to 80, let's say this is 80, it will reach to 80. from 160 segment to it will now send 80 segments, which we are dividing by 2. From there, again, it will start slow. What will do? It will again reach to again 90. If it is finding that, okay, it is okay, then in the next round trip, what will do? It will slowly increase. Let's say 10 segments or 20 segments, it will try to increase, and it will then keep on increasing, keep on increasing. It will keep on increase. And again, it will exponentially grow until unless it is not reaching to a packet loss position. Let's say here again, it is packet loss is happening. Again, immediately it will switch to congestion avoidance, and it will again slowly, it will start sending the segment. So this particular algorithm or concept, we call it as congestion avoidance. And this sudden spike and drop down in the network delivery, we call it as sawtooth, right? Which is based on an algorithm which we call it as AIMD, which stands for additive increase multiplicative decrease, which is a obviously complex word, but this is the algorithm which helps us delivering the packet within the network and ensure that the network congestion is not the cause of failure in data delivery. So that is how TCP handles our packet within the network. And as I mentioned, immediately it cuts off and it then grows if it back on one segment per round trip, and it is keep on doing, right? So there are multiple, again, sub algorithms available in all the operating systems. Like Linux uses something called as cubic, Windows uses something called as compound TCP, which is again another round trip. So Google has invented its own algorithm, which we call it as proportional rate reduction or PRR, which recovers 3 to 10% faster, where we are incrementally, increasing our rate by 2 to 5%. This PRR mechanism can increase immediately 3 to 10%. So where here, if we are increasing like this, PRR can increase like this. Okay, that fast it can travel. So there is another concept within TCP, which we call it as bandwidth delay. What exactly it is? Let's say whenever you are running an app, you have a fast network, but still your application is slow. It can be issue with regards to flow control as well, but bandwidth is also one more issue. To understand the bandwidth delay, let's understand with a simple logic. Let's you have a point A and point B, and let's say water is flowing through a pipeline between this point 2 points. If the pipe is very long, let's say it is over 200 meters, but the water flowing inside it is very low, then what will happen is water can flow very slowly, right? To make it faster, either you have to increase the water size or the volume of the water you have to increase. Similarly, in the network also, from application A to application B, if it is very far, let's say for example for India to US, if the application is communicating and the data is flowing, if the data size is very small and the network wire which is connecting both the servers is very long, then it can take a lot of time to reach, right? So to reduce this or solving this problem, the concept of CDN gets introduced, where the providers like Cloudflare and Akamai, what they do is, instead of keeping both the receiver and sender too far, they try to keep another server or a point where the data can be transmitted from the sender to receiver in the form of caching, and by which the pipeline or the size of the pipeline can be smaller, and even the data is small or data is less, it can flow very faster. Instead of going into the main data center in US, it can stay near, so that the pipeline gets shrinked, and the data, if the data is slow, then it can transmit it properly. So that also being taken care within the TCP, which we call it as bandwidth delay. Now you have seen all the functionalities of TCP and how exactly it works under the hood, and you might be thinking that TCP is a beautiful piece of technology which human has invented ever. That is true, but it has some drawback as well. So when we are ensuring the delivering between a sender and a receiver in a three-way handshake method, so data gets transmitted in the form of packet, right? Packet 1, packet 2, in the form of sequence 1 and segment 1, segment 2, segment 3, right? And it reaches in a sequential manner, right? So if you have 4 packets which is getting delivered to the sender to receiver, for example, during it will be delivered one by one, right? Let's say if in between this packet is getting dropped or this packet is getting dropped during network congestion or maybe some other issue, so during that time, do you think this packet is still getting delivered? The answer is no, right? So how TCP exactly it works is, until unless the previous packet has not arrived, it will not deliver the other packet which is in the queue, because all the things happens in a sequence and it happens in a queue. So until unless if you are not delivering this 3, the 2 will not be delivered. So that is how it works. And this is a drawback of TCP, which we call it as headline blocking. And this is not something that people have not solved it. It can be solved with the mechanism like HTTP2, which already has there. If your application is something which is facing this, so moving it to HTTP2, it can be resolved. And or there is also something protocol called as QUIC, and you can use those protocols to reduce this waiting time, and you can avoid the headline blocking.